I always love seeing new LoRa papers. This one is called DoRA, Weight-Decomposed Low Rank Adaptation, and it's basically an improvement on LoRa. It takes LoRa and basically makes it more accurate across the board. So the accuracy whenever you do downstream fine tuning using a LoRa matrix, or in this case a DoRA matrix, is DoRA decomposition is better than the LoRa decomposition whenever you're doing fine tuning, and it shows promise across the board on the benchmarks that they have. They have it with images, text, I think video as well. So it shows a lot of promise, and it's quite a simple thing that they do, but it shows good performance with a simple kind of change that they make. So yeah, first, what is LoRa? So you've probably heard of LoRa by now. Basically, if you're going to fine tune a model, even if it's stable diffusion now, you don't fine tune the actual model. The first problem is it takes a lot of memory to fine tune the model. So if you know Atom, it basically has to store 3 copies of the weights. So if you have some weight matrix that's d by d, you basically have to store that 3 times. So let's say we have a model size of 7b for llama, then you basically have a 21 billion, you basically have to store 21 billion parameters, which is around 21 gigabytes of VRAM just to store the model. And to do a forward passes with this model, you basically can't do that on a good consumer grade GPU. So it's quite difficult. But if you can instead decompose this matrix into 2 parts, or into a low rank matrix and train that, then you're in a position in which you can actually train this on consumer grade hardware, which is why Llama can be trained, or not trained, rather fine-tuned on consumer grade hardware. So in the attention mechanism, you basically have your queries, keys, and values, and you have 4 matrices. You have your query, or you have your X matrix, which is a S by D matrix, and you have a query matrix, or rather, this will be your weight matrix for your queries, your weight matrix for your keys, and your weight matrix for your values. And you also split this into heads. So this will actually be like H by S by D over H. So your dimensionality is split into multiple heads. Or after, that's actually after. So this is S by D. You then multiply it by these matrices. So these will be D by D matrices, and you get out basically 3 versions of your input sequence. So this may be a tokenized sequence of words, where S is the number of words you have or number of tokens you have, and D is the dimensionality of each word. So just representing each word as a vector. And this will give you 3 matrices. So your queries, keys, and values. And these are all D by D matrices. And you do attention with these, and then you get out your output, and you usually send this through an output matrix, which is also a D by D matrix. So this is S by D. And then you send this through 2 weight matrices, one which is usually this is like a D by 4D matrix, and then you send this through another matrix, which is usually like 4D by D. I don't know why that one's bigger, but whatever. And then you get out, say, a second output. And this is basically your attention layer. And all of these blocks are feed-forward layers. Feed forward, feed forward, feed forward, feed forward. All of these are feed-forward layers. So if you can take these feed-forward layers and basically make a low-rank approximation of them, then train that instead, or fine-tune that instead, then you're in a good state to actually fine-tune this with a small amount of memory. So that's what they do in LoRa. So you take a matrix, move that down here. So you take a matrix, this is W in R of D by D, and you basically are going to decompose this, or rather, this is going to be your pre-trained matrix. So if you know Llama, Llama 2, or variants of that model, you know that it is a pre-trained model. Facebook or Meta fine-tuned or trained it on a ton of data, basically data on kind of the entire internet. And you can think of this matrix here as kind of representing global knowledge of the internet, but not very specific fine-grained knowledge of some certain task. And maybe I want to train it on some fine-grained task or on some downstream task, more specific to what I'm looking for. Maybe I want it to chat with me or something like that. Make it a chatbot or talk to me about some certain topic. I don't know, maybe I want to talk about football or something like that, some sport. So anyways, you basically have this global knowledge and you kind of want to update it, extract some information out of this global matrix to kind of make it better on that downstream task. Maybe you want it to do classification, something like that. So you want to fine tune this matrix. However, storing three moments of this matrix is not efficient. So you break this into two matrices, B and A, where your A matrix is going to be I'll put it over here. Yeah, A is going to be a R by D by R, that's a little r, and this is B is in R of R by D. And you basically, since these are feed-forward layers, they only operate token-wise, so I'm just going to draw a token here, and this is just the normal DoRA diagram. So this is going to be a token for one of the words that we have, which is just a D-dimensional vector. And you basically send it through both of these, and you get out two outputs, which will be two vectors. And then you just add them together, and this gives you your output vector, like this. And this will give you your output vector. So basically what this operation boils down to is your output is going to be equal to your weight matrix times your input x. So this will be x plus AB times x. And organize this in the way that makes these matrices multiply happy. However that may be. I'm going to write it out like this because it's an intuitive way to look at it. But basically, you multiply it by this W matrix, which is your old matrix. This is your old information that you learned from the entire internet, your Llama 2 matrix. And this is going to be your new weights, where A is initialized from a normal distribution with zero variance and some standard deviation. And this is initialized to a zero matrix. So remember, the goal is to fine-tune our model. And we basically add these adapters here to every weight matrix that we have. So we add an adapter, both A and B adapters to every weight matrix we have. So this weight matrix, this weight matrix, this weight matrix, this one over here, and so on. Oh wait, it was actually this one, not the A matrix. Anyways, you add it to all your feed-forward layers. And essentially what the idea is you're going to train these layers here, your A and B layers, and you're going to keep this one frozen. So if we look at this in memory, this will require, to just store the thing, it'll require D by D to just store it in terms of memory, not the moments at all. So this will be D by D plus 2 D by R. So this is actually more parameters than the original model. However, whenever you're storing the moments, in the original model, it would be 3 times D by D. Now that's a large amount because you have to store 2 moments of your weights. However, in this case, you only store one version of your weight matrix here, and then you store 3 moments of these here. So it would be 3 times 2 times D by R. So this is going to be a lot smaller if your R is small, and you can pick R to be, say, 1 or 4 or 32, which is significantly smaller than D, which is usually 1024. So essentially, your net memory is going to be way less, and usually the number of trainable parameters, these parameters here, is going to be a lot smaller. It's going to be, if you've trained or fine-tuned a Llama model, it's like 0.01 or something like that, some really 1%, some really small amount. So that's the idea. You're storing these small weights in memory and only train those, which allows you to have a small memory footprint, allowing you to train this thing well. So it's not going to take, it'll take 7 billion plus a few more parameters. So maybe in the upper bound, it'll be like 8 billion if you have a really large R, but usually it's a lot smaller than that. So these matrices are very small, and it allows you to train these models. Now, a second nice part is after you fine-tune these models, I keep on mixing those up, sorry. This is fine-tuning. You're not training a model with LoRa, you're fine-tuning it. A nice property is you can actually combine these weight matrices after you're done training. So once you're done fine-tuning your A and B matrices, you can combine A and B with W. So I can reorganize it or rearrange it like this, W plus AB, X, and then call this W prime X. And I essentially store this in memory. And after you're done fine-tuning your model with the A and B matrices, you can store a matrix with the exact same amount of memory on disk. So it doesn't take up any more memory than it did before, once you're done training it on disk and whenever you're doing inference. So second nice property about LoRa. Now, this paper basically takes this and it brings it up one level. So the idea is that you can decompose this matrix, the original weight matrix here, into direction and magnitude, because it's just a vector, and vectors are defined by magnitude and direction. So what you can do is you can say, well, our weight matrix is equal to some magnitude, and our weight matrix is going to be the d by d matrix, this one here that we want to freeze and we want to decompose it. So this matrix here is going to be equal to some matrix, so some magnitude times the matrix times the unit vectors. So this part here, well, I'll write it out the second way. And the way you can represent this is by the, well, magnitude of every column vector times the normalized vectors. So if I write it out this way, this will be our magnitude here, because this is the definition of magnitude. It's just the magnitude, the L2 norm or magnitude of every vector. And this here is the unit vector, which basically defines the direction. So if I have a bunch of vectors here, like this, then the magnitude basically defines the length of them, like this. It defines the length, and the direction, well, it defines the direction on the plane here. So what is basically the direction, or where is it pointing? So it gives you it would basically put it on the unit circle or unit sphere in whatever dimension that is, and just say, well, that's the direction that it's pointing in. So you break it up into magnitude and direction. And intuitively, you can break it up, and this just gives you the same exact equation. So I can just cancel these out, and then it gives you your original weight matrix. So we have successfully broken this into magnitude and direction. Now, what they do is they say, well, as we're fine-tuning this, or as we're fine-tuning the LoRa model, or the model with LoRa weights, how does the model update? So how does the magnitude and the direction change? They define two equations here. Let me move this over. So we have the magnitude and direction for our weight matrix. And like I said, you can basically define a new weight matrix here after you're done fine-tuning LoRa, and then basically put the weight matrix together, update the weight matrix with the LoRa weights. And you can find the magnitude and direction of that. And you can do that in intermediate stages of the model as well. Now they want to examine, like I said, the change in the magnitude and the change in direction. So the change, or rather the average change in magnitude. So your weight matrix is defined by a set of vectors. So they take the average over all those vectors for your weight matrix, for some arbitrary weight matrix in the model. And they take the average magnitude. So this is just the magnitude definition. It's the magnitude of the current weights. So the current weights being fine-tuned at some time t. And this is just the original magnitude. So they're basically saying how far is the magnitude of the current vector from the original vector. And then they also look at the distance, the change in the change in direction, and you can do that by the cosine similarity. So cosine similarity is defined like this. If I have a red vector here, say that's our original vector, that's w0, or w0, the nth vector in w0. And then I have another vector, say it's this vector here, the blue one. Then since they're orthogonal, it'll give you a similarity of 0. They're as dissimilar as possible. That works in any dimension, and it also works the other way as well. You can go down. So as long as there's a 90-degree angle, they're as dissimilar as possible. Or rather, if they're orthogonal, they're dissimilar as possible. If I have a vector here right on top of it, then that's a 1. And there's basically an interpolation between the two. If I go all the way across to the other side here, then I have a value of -1, meaning that they're similar, but the direction is different. So they're similar in that they're on the same axis, but the direction is opposite. Now, here they don't remove the -1. I think it should actually be the absolute value of the cosine similarity, so that it's between 0 and 1. Because it wouldn't make sense whenever they invert it. But basically they invert it to make it more intuitive. So whenever you invert it, you say it's a value of 1 if it's as dissimilar, if it's very dissimilar, and it's a value of 0 if it's very similar. So yeah, that's the idea of the change in direction. So basically, you start off with the vector here on top of the original vector. So if our original vector is red, and our new vector is blue, then you start off in the same spot because you initialize to 0. You initialize your matrix to 0, meaning that there is no update. You start off in the exact same spot that your original weights were at. And slowly you'll probably move this direction. Slowly you'll probably move, the vector will move away from what the original vector was like. And they want to examine that. So that's the change in direction and change in magnitude. Now, whenever they examine it, they see that that whenever you fine-tune a model, it basically has this decreasing slope. So they plot the change in direction versus the change in magnitude, and they notice a bunch of things. They say, well, as the change in direction increases, there's a larger change in magnitude. So as the vector changes direction more, so as it changes direction more, the magnitude decreases. So there's kind of an inverse relationship there. And that's what they notice. They also notice a second thing, which is high variance. So you can see there's very high variance here across the board, across all the changes in direction. And this is basically your 0 change in direction and 0 magnitude. So as you increase your magnitude, or as you increase your change in direction, as it becomes more different from the original vector, the magnitude decreases. So the magnitude gets smaller, which is interesting. Now, if you look at the LoRa weights, as the vectors get further away from the original vector it was at, the magnitude actually increases. So they say that and it also has low variance. You can see if you go across the slope that they have, it has very low variance. So those are two things that they notice, and they say this is a problem because LoRa is supposed to mimic fine-tuning with the same or with a smaller number of parameters, but it doesn't in this case, or in this sense. The two are clearly different. And they claim if you can match this here, if you can basically increase the direction while decreasing the magnitude and have high variance, so basically mimic what fine-tuning does, then you can get better performance, because the goal is to mimic fine-tuning just with a low rank adaptation. And that's what they do with DoRA. So whenever they introduce DoRA, or whenever they use DoRA, it actually does have this decreasing slope with higher variance. You can see the variance is higher here. It's not as nice as fine-tuning, but it's definitely higher. And there's definitely an obvious, if you increase the difference in direction, you decrease the magnitude. Though these are also on different scales. But that's the argument that they're making. So they want to mimic it in a better way. DoRA, they want the low rank adaptation to mimic the fine-tuning adaptation in a better way, according to the change in direction, change in magnitude property that they saw. So they do this by saying, well, we already have the magnitude and direction here. Why don't we just train that? So that's what they do. And they train it with LoRa. So if I go here, I'll erase this. There. So if I go here, this is how they train it. So our original equation was W is equal to, it was the magnitude of W times W over magnitude of W. So magnitude and direction. And basically they say that they can update this by taking the magnitude. So they just directly update the magnitude. They keep V frozen and keep M trainable. So and then the directional component is updated through LoRa. So they basically decompose the matrix into this here, decompose it into magnitude and direction, and they basically directly change the magnitude, just directly change it using by fine-tuning that, because that's just a vector where each of these corresponds to one of the vectors in the matrix, so it'll be a d-dimensional vector. And here, this is going to be a matrix, so it'll be a d by d matrix, d by d. And since this is a d by d matrix, you can just, well, rather this upper part will be W0. W0 is just a d by d matrix. It's your original matrix. You can just fine-tune that using LoRa. So you just add your A and B matrices and initialize them like normal. So A, B, initialize this to 0, initialize this to a normal distribution. They actually, I think they use a different initialization, but same idea. Initialize this one to 0 so that the addition, or so that it doesn't add anything initially. And then you can just normalize it as it's training. So just L2 norm over the column vectors. So this is going to be what you're training, and you just train this like normal using normal fine-tuning procedure. So that's all it does. It basically just trains the magnitude, changes that, and changes the weight matrix by a LoRa matrix. And the nice thing is you can also bring this back together. So like with the original LoRa, how you can decouple it and then couple it. So you can decouple it into the two matrices and then put it into one matrix. In the end, it'll take up a small amount of memory whenever you're training it, and then you can put it back together into the original shape that it was. So by just adding these together. So yeah, this is basically the idea. All you're doing is decoupling it, magnitude and direction, and training the magnitude and direction independently from each other. And you train the direction using LoRa because it's a matrix, and you train this just normally because it's a vector. So it adds a tiny bit more parameters over LoRa. LoRa would basically just be this upper part here. That would basically be LoRa. It adds this part here, so basically d more parameters to train, and this part here, which basically makes the gradient more annoying. They mentioned that down here. That you basically have extra memory during backprop, and to address this, they suggest treating the denominator in the equation as a constant and attaching it from the gradient graph. So basically, they just treat this as a constant. So in the gradient, they treat it as a constant. So they basically apply a stop grad here. So stop grad of this here. And that way, the gradient doesn't become larger than one would hope. So that's the implementation they have. Now, the idea is if you do this, it should give you something similar to this fine-tuning procedure here. This DoRA should give you that. I mean, you can already see that here, but that's the intuition, that it should do that because it can directly manipulate the change in direction and change in magnitude. So it should be able to be closer to the fine-tuning procedure and mimic it better than LoRa can. They show that empirically. They also kind of have a proof for that, saying, or if I go down here, here. So they have this long proof saying, oh, if you look at the gradient, you can see that things happen. It's a big proof, and they conclude that basically the gradient of the loss, so the gradient of the loss with respect to the magnitude of S1, where S1, if I go up here, involves a smaller directional update. So it has a small directional, so this is basically the gradient of the magnitude of a small directional update, and you take the absolute value of that. It has a larger magnitude than a larger directional change. So all this to say, if you have a larger directional change, then the update in the magnitude decreases. And if you have a smaller directional change, or if you have that was wrong. If you have a large directional change, then the loss with respect to the magnitude is smaller or is larger than if you have a smaller directional change. I think I'm messing up my words there, but basically you have an inverse relationship here. A larger directional change gives you a smaller magnitude change here. Yeah, S1 was a smaller directional change, and it has a larger magnitude gradient. So the magnitude changes more. So that's the basic idea. You have this inverse relationship here, which gives you this here. So they kind of prove that as well, that they don't just show it empirically, but they show it via that proof that they had, which shows that it has an inverse relationship. So that's what they were hoping for, and that's what they got out of the DoRA decomposition. I hope that makes sense. I kind of scuffed up the explanation of this, but basically it gives you the inverse relationship you're hoping for. Yeah, so that is that. And it's really simple. All you do, this whole operation is pretty simple. Just decompose it into magnitude and direction, and train the direction using LoRa, train the magnitude normally. So that's the idea, and yeah, that's what their method is, and it shows promise if we look at the results. That's a smaller version of the chart that they have down here. So if I go down here, I kind of like highlighted which ones were the best. I think there were like 2 or 3. 1, 2, 3. Yeah, so there were 3 different ones where LoRa performed better, 3 different fine tunes where LoRa performed better, and the rest DoRA performed better. So in general, DoRA performs better on Llama B fine tuning, so on text fine tuning. According to this chart that they have here, and it performs significantly better. Like if we look at this one here, if we have a really small R, and we look here on this benchmark bull Q, then the improvement is massive, and you basically have the same amount of parameters. The extra parameters are from the magnitude that you add, because you have that extra vector you have to train. But yeah, if you look, it actually does really well with the smaller R, while LoRa does significantly worse with the smaller R than DoRA does, which is quite interesting. But in general, it does a lot better. They have a bunch of other benchmarks. If I go over here, they say, or they look at image video understanding, and if you look at these, it does better on average for the comparisons that they have for the benchmarks that they have. They put it on a bunch of benchmarks. And then visual instruction tuning, they also show that it does better there, with the same amount of parameters, basically. Yeah, so it does pretty good, and it's basically the same amount of parameters. So the intuition was pretty much correct. If you wanna, you can basically mimic the fine tuning behavior with the direction and magnitude, with the change in direction and magnitude, and it'll perform better. The intuition behind that was apparently right. One other thing I wanted to show was kind of the robustness. So if I go here, DoRA seems to be a little more robust to rank. So I kind of showed that down below with the results, and they kind of show that here with some cool graph. With a lower R, LoRa seems to perform worse, and DoRA seems to perform better. And DoRA seems to perform better overall, but with a lower R, it seems to really show the difference in performance between LoRa and DoRA. Yeah, and then they show it also against Vera, which is apparently some other LoRa variant, and they do better than Vera. Yeah, so that is the procedure. Basically, just split it into, you take your weight matrix, split it into magnitude and direction, train the direction and magnitude, combine it back together, get your merged weights, and you got your fine-tuned model. Hope that is hopefully better than a LoRa fine-tune. So yeah, that is DoRA.